All right, our next lesson here is waves in 2 dimensions. So 2-dimensional waves share many properties of 1-dimensional waves, but there are differences in how the properties manifest themselves. In addition, there are several new properties like refraction and diffraction that we need to discuss. So waves in 2 dimensions, like ripples on water, are worth studying because we can readily observe all kinds of different wave phenomena by generating these ripples. A common ripple pattern is a straight wave fronts that are moving in a given direction. So what we're looking at here is like the crests on a ripple moving outwards. Now I recognize that typically we will see those in a circle because they were generated from a point, but we are going to look at them as just straight lines in this first case. So the crests of the waves are the tallest point in the wave, and then the troughs are the lowest point, and those are in between here. What we've labeled, it's got a question mark here, the distance between crest to crest or the middle of a trough to the middle of a trough would be our wavelength. This is called a wave front diagram. This is the same thing as a wave ray diagram. Our wave is moving in this direction, so we can draw it as just a ray as well to simplify things for our work. These mean the same thing when we're talking about 2-dimensional waves. This is just a simplification of something moving outwards like this. Okay, we kind of talked about this, the waves on the wave front diagram represent the crests of the waves and the arrow indicates the direction of its motion. The wave ray diagram is equivalent. It just represents a set of wave fronts moving in that given direction. Again, it's a simplification. Okay, reflection. When a wave strikes a solid boundary, it will be reflected by the boundary. This is similar to a basketball bouncing off of a floor. So when our waves come in towards our solid boundary. So if we were talking about water, this would have to be something totally stationary in water that wouldn't be able to bob up and down. So like, I don't know, an island that goes straight up and down. There's no beach leading into it, or I guess like a cliff. So our waves come in, if they come in at an angle, so the wave is kind of coming this way, it strikes the boundary and we're going to get a reflected wave this way. To simplify this, because we don't draw lines when we're talking about waves, we're just going to draw that wave ray. Okay, so our incident wave comes in at this direction and reflects at this direction. The way that we measure our angles is we measure from the normal. Remember, the normal is a 90 from where this strikes. This is because if the boundary is curved rather than straight, this would have a different angle here. So we just use our normal at that moment or that point where it strikes. Okay, so again, these were wave fronts. These are wave rays, but these both represent the same thing, same representation. All right, so incident wave is our incoming. We measure this angle, theta incident, from the normal, and we measure this angle, theta reflected, from the normal as well. The angle of incidence equals the angle of reflection. So these two are always equal. All right. So a wave is incident on boundary A and reflects to boundary B. What is the angle of reflection at boundary B? Now we needed this diagram. I'm so sorry. I totally missed this and I deleted it. So I'm just going to quickly draw it and I want you to draw it as well. Okay, so this is our original setup, and what we see is we have this incident wave coming in and striking surface A at a 50 angle. Remember, the angle of incidence is measured from that normal, so 90 degrees from A to where the wave is hitting. A is joined to surface B here by a 110 angle. So remember, the wave will reflect with the same angle of incidence. So our wave here will reflect off of A with an angle of 50 as well. Now it's hard to draw, sorry. So meaning this angle here will also be 50 degrees. So it's going to strike B at some angle over here as well. We can calculate the rest of this angle, which is helpful because we then have a triangle. We know that all angles in a triangle add to 180. So this angle here, I'm going to call it, I don't know, alpha. So alpha is equal to 90 degrees, take away our 50, and so that's equal to 40 degrees here. All right, now we can find this angle. I should use a different color. And let's call this theta. So theta is 180 degrees, which is what all angles in the triangle must add to, minus 110 minus 40. So theta is equal to 30 degrees. Now remember, we measure our line here from the normal. So let's do that. We'll draw our normal in here, and this is our answer, X. Okay, what is the angle of reflection? Remember, that's always measured from the normal, which is 90 degrees to that surface. So 90 degrees, take away our original theta here, which is 30. We get that our angle of reflection, X, is equal to 60 degrees. Okay, that means that this will reflect at 60 degrees here as well, because the angle of incidence equals the angle of reflection. All right, refraction and reflection are different. So waves traveling in a consistent medium will have a consistent frequency, wavelength, and speed, meaning they're traveling through rock or through air. The medium doesn't change. We don't go from one type of rock to another or more dense to less dense air. However, if the wave enters a region where the medium changes, like air to water or deep water to shallow water, the speed and wavelength of the wave will change while the frequency remains unchanged. The change in speed and wavelength is due, if you recall to the previous lesson, to the fact that they depend on the medium. So remember, fast versus slow, dense versus not. The frequency depends on the source of the wave, and in the medium, it is not the medium, that it is traveling through, so it does not change. So, whatever all of this is, it doesn't really matter. We get that the frequencies were equal, so we can set them equal in two of our universal wave equation here, and we get that V1, V2 is equal to lambda 1, lambda 2. Now we don't have this, I can't remember, sorry, if this is on our formula sheet or not. Yeah, it kind of is. It says N1, 2 over N1 equals V1, V2, lambda 1, lambda 2. Okay, so it is on our formula sheet. Using water waves as our example, what happens when a wave moves from a high speed area to a low speed area? So as a wave passes from a deep water area to a shallow water area, they slow down and the wavelength decreases. So waves coming in from, let's say, deep water out here, they pass into a shallow water area over here. They slow down, so their speeds will change, and the wavelength will decrease. So if the wave enters a different region at an angle, the wave will bend depending on whether it speeds up or slows down. So the wave is coming in here, and it's coming in fast, and it's starting to slow down at this boundary. Okay, so the wave is coming in and it slows down, so it gets pulled backwards here. It's coming in and it hits the boundary, it slows down at the boundary and slows down at an angle here. Okay, our wavelengths decrease, and again, our waves become slow. if the waves are coming in slow and hit a boundary where they are able to speed up, they come in slow, they hit this boundary and they speed up, so they start to move at a different angle. All right, this is tricky. All right, so I looked at this analogy and it really helped me to understand what was going on, and we can go back to our original diagrams. Consider the following analogy. A platoon of soldiers march in formation across firm ground until they march at an angle into some mud. The speed in the mud is slower, therefore the lines of soldiers will bend due to the change in direction caused by the change in speed. So we're looking here, they're on firm ground and they're moving kind of at an angle here. This is their motion or movement. Okay, so they're at firm and they're able to move quicker. Now, once they hit the mud, they slow down. And so once they hit the mud, they start to become closer together because they've slowed. Okay, so if we look here, they're moving quickly and they hit the boundary and they slow down. So they're kind of held back and they become closer together. And because of that, they start to bend, or what appears to be a bend. Because they are closer together here, they don't have this same angle between them. They have a bit of a different angle. So when they hit the boundary, they slow down in the mud and they are kind of held back. If it's opposite, they're moving really slow, they're in the mud, and then they get to speed up, they will be further apart and they will have a faster speed once they get out of the mud. Okay, I thought that was really helpful to visualize, so I think of that when waves are hitting a boundary at an angle. So an easier way to draw and visualize refraction rather than drawing all of our wave rays, our wave fronts up top here, we can draw our wave ray. So an incident wave, remember, it's hitting this boundary here at an angle. We measure its angle of incidence from the normal. So it's in a fast, medium below here. So this is fast. And when it hits this boundary, it slows down. So technically it should be continuing at this angle, but because it's slowed down, it's brought a little bit closer to our normal. So these are not equal if the mediums are not equal. Okay, so if we have different medium here, we have different angle of incidence and refraction. All right, now if we have our incident wave that's in slow here, medium, it would technically continue in this direction. However, it's able to speed up, and so it will move at a different angle. Our angles are not equal. So it says here, when a wave bends towards the normal when it slows down, so our angle of incidence is greater than our angle of reflection, and the wave bends away from the normal when it speeds up. In any case, the side with the greater angle has the faster wave. So check out the video here. I think that that's helpful. I think that these videos do a good job of explaining a lot of this and showing examples of it. So again, the angle of incidence and the angle of refraction are always measured from the normal.